We were discussing about control over lossy network, so I just wanted to remind you of what we did last time. So in the previous lecture, we had talked about xt plus 1 equals to axt plus alpha t but plus wt. This is my state equation. Alpha t is basically Bernoulli alpha bar, and we had assumed what we were talking about is if rho a is greater than 1, then there exists a alpha c bar such that is if alpha bar is greater than alpha c bar, then alpha bar is less than alpha c bar, then st was going to infinity, where st is the output of the Riccati equation. Can someone remind me what the st recursion is? I think it's a st a transpose plus r minus alpha bar. What do we have after that? No, this should be q.
No, S is ST1. S underline T plus 1.
Is this correct?
We used T plus 1 last time.
Oh, I see. Yeah, of course. I'm sorry. Right. So actually, then I have to change this to st going to infinity. Instead of saying that, I need to say that if capital T is very high, then S0 is going to be close to infinity. So this is the backward recursion equation, and I'll have to make this a bit more precise. Let me write it the following way. Then S infinity is equal to infinity, and S infinity is fixed point of the Riccati map. So this is my Riccati equation, and as I keep running this iteration again and again in a backward fashion, and I let this t, I let this whole thing, I run this iteration for infinite number of times, then S infinity will be the fixed point, and that will be equal to infinity in this case. And what this essentially implies is that the system is unstable. In other words, xt will go to infinity as t goes to infinity. Okay, so last time we were talking about this specific example where you have a car or a truck which is going on a curved road. The action is the steering angle that we want to pick, and in some cases it could also be the velocity. Velocity is also something that you are, acceleration is also something that you are changing. But the important part here is the steering angle part. So your action is the steering angle, your xt is the deviation from the center point. Okay, so that's how this thing works. And if you have a curved road, like you're driving on a mountain or you're driving on a curved road or a curved highway, then your rho a is greater than 1, which means that if you do not control, if you set your ut equals to 0 at all points of time, then in that case you're basically going to go on a tangent. And as you can see, if your ut was 0 all the time, you can continue to go on a tangent, and if you look at the distance, this xt goes to infinity. So that tells you that this particular system is unstable. Okay, so rho of a is greater than 1 in this particular case. And what this statement is saying is that there exists a critical probability. So what is happening in this case? Under the attack, the steering angle information that I'm sending from my steering angle all the way to the vehicle's wheel, there is an adversary who is dropping that packet. How can they drop the packet? Well, we've seen that particular attack in the Jeep Cherokee attack, wherein the legitimate information was not being sent from the driver's side all the way to the actual wheel. So that was the attack. So keep that attack in mind, the Jeep attack in mind. And now you have a critical probability or critical average probability of transmission, such that if your probability of transmission is less than the critical transmission probability, then your system will be unstable and your xt will go to infinity as t goes to infinity, which means that this particular distance between the center of the road and the position of the vehicle, this will go to infinity as t goes to infinity, which is an undesirable behavior of the system. So this is a kind of attack where there is a fundamental limitation of the attacker. If the attacker is more powerful, in which case your alpha bar will be less than the critical probability, in that case your system will almost surely fail. Now imagine if you are driving on a mountain. I don't know how many of you have driven on a mountain, but typically mountain roads are like this, okay, at many junctions. And so if you are able to, so see, you can see that the curve is actually extremely, the radius of the curve is very small, in which case this rho a is actually very, very large along these curves at this particular point. And so if you are able to, if the attacker is able to drop the packets exactly at these locations, your car will go in the valley because of the fact that you are not able to control it. So the alpha c here, so alpha bar c here will be maybe 0.1, but alpha bar c here would be 0.9. Okay, so there are some, if you are driving on a mountain, you will have situations where this alpha bar c itself is changing because the curve of the road is changing over time. And so you want to make sure that at every point of time you're able to send information above this critical probability. You always have to be above the critical probability. Okay, so you want to always be above this alpha bar c. Now so this is the so of course I'm talking about the vehicle here, but this kind of result holds for any unstable system. So as long as you have an unstable system, there will exist a critical probability such that if you are below the critical probability of transmission, your system will become unstable. That's the takeaway that I want you to take back home with this particular result. So yes, we have done it for linear system. Yes, we are writing the linear system terminologies here, but take that as a takeaway point, that unstable system, if you have an unstable system, you definitely want to make sure that your transmission probability is above a certain threshold. If you have a nuclear power plant, you want the probability of transmission to be very high if you have a grid, like a regular electric grid. You want to make sure that your ability to control is not hampered when the adversary is attacking the system. And you will have to make a lot of design decisions in order to make sure that your alpha bar is always greater than alpha bar C. Okay, any question? So the goal for today is to talk about estimation over lossy network. So we have talked about how to control over lossy network. Now the goal is to talk about estimation, and what we will see is that we come up with exactly the same result. We'll have exactly very similar result even for the estimation over lossy network. So I just want to cover that part in today's class. So let me erase this side. So there is no loss of control action. I am able to control properly. Now my yt is beta tcxt plus vt, and now my beta t is Bernoulli beta bar. Okay, so I'm now able to control reliably. There is no problem with controlling the system, but there is possibility of packet drop when I'm observing the system. So I have a sensor, I am measuring the sensor reading, but now because of the adversarial attack, I'm not able to reliably read the sensor reading. So there is a probability with respect to which the packet might drop and I may not be able to make any observation. So yt will be equal to 0 in that situation when the packet drops. I think we probably have this situation. So it's not like we get Vt, we just don't get any packet. So yt will be uniformly equal to 0 in that case. So previously, we studied this notion of Kalman filter. And for the case when beta t was identically 1, which means that there is no unreliable communication aspect, like the communication is always going to go through, there was a very simple estimator that we had, which is x hat t plus 1 equals to a x hat t plus b ut plus l yt minus c x hat t. This was the estimator that, yeah.
We were using Gaussian.
We are all using Gaussian for now.
Why we're using Bernoulli now?
Oh, Bernoulli is because it's a packet drop. It's a packet drop probability. So it's a 0, 1. You cannot have any other value. Either you get the information or you don't get the information. That's it. Okay. So Wt is still Gaussian, Vt is still Gaussian. Only beta t is Bernoulli at this point of time. So this was the what is that called? This was the estimation scheme. L was called the Kalman gain. And we wanted to make sure that our estimate is as close to the true value as possible. Okay, so now we are in a situation where beta t is no longer identically equal to 1. We may have a situation where the packet is going to drop, and now we need to find how do we estimate this particular system. So the theory is very similar. So in the previous class, what we did was we had this optimization problem that we needed to solve. We went through the dynamic programming equation and we were able to solve the optimization problem. It turns out that in the case of Kalman filter as well, I know that we haven't done the derivation of Kalman filter in the class, so I don't want to do the derivation today. But you are basically solving an optimization problem, and after solving the optimization problem, you get the optimal Kalman gain and a filtering equation which tells you how to update the estimate of the state. So today I'm going to write down what the Kalman filtering here is going to look like under the TCP protocol. Okay, so this now we are beta t is not equal to 1, and I am looking at the TCP like protocol for which I want to write down the Kalman filter. So in the TCP like protocol, what is the information set that the estimator has at time t? So I know y0 to t, I know beta 0 to t. These are the two information I have because I get the acknowledgement of whether the information was received or was not received. This is the information that I have. And now I'm going to define a few quantities . Okay, so here what am I doing? This is my estimate of the state given the information at time t. This is the estimate of the state given the information at time t. So look at the conditioning variable here, it's I of t. I of t is all the observations I have received so far and all the packet drops that packet drops or packet successfully transmitted, that information until now. And so I'm looking at the next state estimate, the current state estimate, the next state error, the covariance of the error. This is the conditional covariance, by the way, of the error given all the information I have seen so far. And then I'll have a ET given T and PT given T. What exactly is the objective function in this case? What is it that we should be minimizing in the case of filtering, Kalman filter, when we are trying to estimate the state? So if you think about it, what we really want is x hat to be as close to x as possible at every point of time. So what we really want to minimize is the covariance matrix. I want to minimize the covariance matrix, or in some cases trace of the covariance matrix. That's what I'm trying to minimize, the trace of the covariance matrix, in order to figure out what the optimal estimator is going to be. So Kalman filter, this is the term that I want to have I want to make sure that this particular term is as small as possible. My error covariance is as small as possible with Kalman filtering. So if you set it up as an optimization problem, you can solve it. It's a bit difficult optimization problem. I'm not disputing that. It requires quite a bit of machinery to be able to optimize this particular covariance matrix. If you take a course in stochastic processes, I think by the mid-semester or by the end of the semester, you will know how exactly to minimize the covariance matrix in order to get the filtering. So that's why I'm not covering it in this class, because it requires order of magnitude more machinery to be able to derive Kalman filtering from first principles. So here is how the Kalman filter for this particular case will evolve. So the first step, it's called the innovation step. And here you have x hat t plus 1 given t is equal to a x hat t given t plus b of ut. Maybe I should add u of 0 to t as well in this case, since we definitely know the control action as well. So just make a small change. I have added u0 to t minus 1 in this case, because that is obviously available to the estimator. And then p t plus 1 given t is given by a pt given t A transpose plus sigma w. So this is the innovation step, and then step 2 is known as the correction. Correction step. X hat t plus 1 given t plus 1 equals to and this is my Kalman gain. I think it's important to understand what all things we are doing here. So let me start from the beginning. So this is my state update equation. This is my observation equation. I'm not getting the observation sometimes, I'm getting the observation sometimes. So the drop probability, packet drop probability is 1 minus beta bar, and the packet successful transmission probability is beta bar. Okay. We have a TCP-like protocol. What that means is I am able to observe beta 0 to t. I am able to know whether the packet was successfully transmitted or not transmitted. So based on this information, I need to estimate what the state is. So I've defined a bunch of quantities xt plus 1 given t. So what's my next state going to be given the current time step? What's the next state going to be? What's the current state is given the current state? Current information. Yeah, okay. So u goes from 0 to t here. So there are multiple, there are two steps in this entire process. In the first step, I'm going to forecast this is what my state is going to be like. So I know what my current estimate is. I know what the A and B matrices are, so this is my forecast. So this is my forecast, and this is the error probability, the error covariance matrix of the forecast. Okay, so this is the forecast error covariance. Now I observe this new information yt plus 1. I have the estimate, the forecast that I had. So this one is the error in the forecast. So this was my forecasted observation, but this is the actual observation that I have received. So this is my error in the forecasted observation. I'm going to multiply it by the Kalman gain, which is given by this expression. Now beta t plus 1 here basically refers to the fact that this packet might get dropped, in which case I don't have anything to base my forecast on, and my x hat t plus 1 given t plus 1 will be exactly equal to my forecast. So if I don't receive any observation, so beta t plus 1 will be equal to 0, in which case my estimate is the same as my forecast because I don't have anything else to update my forecast on. On the other hand, if beta t plus 1 was equal to 1, then I could actually improve my forecast here, and this is the amount by which I'm going to improve my forecast is given by this matrix multiplied by the error in the forecast, which gets added to my forecasted estimate and gives me the updated estimate. So this is my Kalman gain, the optimal Kalman gain. This is the truly optimal gain that minimizes the error covariance matrix. And then this is how I'm going to update my error covariance matrix. So this particular term, pt plus 1 given t plus 1. So this is the error covariance matrix at time t plus 1 is error covariance forecast minus, if I receive the packet, then it's going to get If beta t plus 1 was equal to 1, which means that I received my packet, then this forecasting error will go down, or the error covariance will go down by this much quantity. On the other hand, if beta t plus 1 was equal to 0, then this particular term vanishes and my forecasting error covariance is the same as, the error covariance at the next time step is the same as my forecast error covariance at the current time step. Okay, so that's roughly what is happening here. So you forecast first, and then based on the updated information, so that's why it's called the correction step. So innovation, it's not the usual innovation that we hear colloquially. Typically in the case of random processes, innovation is basically some sort of forecasting that is happening. That's what is called innovation in the random processes class, which I know many of you may not have taken, but there is a random processes class in this department, which you can take, and of course it's also there in statistics department and math department. So anyways, the innovation basically means forecast. You can as well call it a forecast step. So you do the forecast and then you update the forecast. You correct the forecast based on the updated information that you have received. Okay, if you expand this particular term, you will actually notice that this is the same, it looks very similar to the term that we had earlier in the context of control. So let me write it down. So let me call this Pt plus 1. Let's call Pt plus 1 equals to Pt plus 1 given t plus 1. So I don't want to write the big expression. So what I get is Pt plus 1 equals to A Pt A transpose plus sigma W minus beta t plus 1 Lt plus 1 is okay. So this is my state update equation. I did the innovation step, I did the correction step. I really don't care how my UT evolves. I don't care about UT here. I'm not optimizing UT at all. This is just, I have a control policy. Maybe it's a PI controller, maybe it's a lead lag compensator, maybe it's a linear controller doesn't matter. I have some control action. I am doing the estimation at every point of time. I'm doing the innovation step. I'm doing the correction step. Turns out my error covariance matrix is going to update according to this particular fashion. One thing I want to point out here is this is PT plus 1, this is PT, but this is PT plus 1 given T, PT plus 1 given T, and PT plus 1 given T. So just make sure that you note it down correctly. And here, this particular process is actually a random process because beta T is IID Bernoulli. This is IID Bernoulli beta bar. Now the question is, what happens? Let's assume that rho A is unstable. Rho A is greater than 1. What will happen if this term is always 0? If beta T plus 1 is always 0, which means that there is no observation coming in. There is no observation coming in, so beta T plus 1 is equal to 0, and my rho of A is strictly greater than 1. What exactly happens to PT plus 1? Can someone tell me what happens to PT plus 1, PT as t goes to infinity? It'll blow up. Okay, so PT will go to infinity. Why will it go to infinity? So I have P0 and this A is greater than 1. So let's assume the scalar case. So this A is greater than 1. So you have A square PT here. So given P0, this is getting multiplied by something greater than 1, and then I'm adding a small number to it as well. I get P2, and then I do the same thing over and over again, and very soon you will see that PT is actually blowing up. So you have an unstable system. You are driving a car on a curved road, so you have an unstable system, and there is no information coming from the road. So your camera is all blank. You're not getting any information from the camera. What is going to happen to your error covariance matrix? The error covariance matrix is going to go to infinity. What does that mean? You don't know. You will never know where your state is at this point of time because you cannot see. So imagine driving on a mountain with your eyes closed. That's exactly what this means. Beta T plus 1 equals to 0, which means you're not getting any information from what's happening on the road. So what happens if we drive the car on a mountain with our eyes closed? I'm sure it's not a fun experience. And what does it mean mathematically to not have a fun experience? It means that PT is going to infinity. Okay? The error covariance matrix is going to infinity. It means my error could be anything. My error could be infinity. So my estimate could be completely off from what my actual state is. So this is equivalent to saying that ET given t is equal to infinity, which is equivalent to saying that xt minus x hat t given t equals to infinity. So my estimate and my by the way, I'm writing equal to infinity, but what I really mean is going to infinity. So xt minus, so my current state minus the estimate is actually going to infinity. So that's what it means for PT to be going to infinity. So we are seeing something similar, some sort of similar behavior here, that if my state is unstable, if my dynamics is unstable and I don't receive any information about the system, my error is going to go to infinity. Now, what the result is that there exists a critical transmission probability above which you will have a stable error covariance matrix and below which you will have an unstable error covariance matrix. So let me write that down formally. If rho A is greater than 1, then there exists beta bar C such that if beta bar is less than beta bar C, then this is the critical probability such that Pt goes to infinity. Yes.
So in common filter, if we set the process covariance equals to 0, which the estimation will be approach to the model we set.
If your initial estimation error is 0?
No, the process covariance
Yes.
is 0. Like I said, the Q value is 0.
Okay.
So then my estimation value will based on the model prediction.
That's right.
Then would I be still affected by the P covariance?
Yes, it will be. So there are few things that you should notice here. So there is my sigma V and then there is my sigma W. So sigma W comes from the actuation noise and then sigma V comes from the observation noise. So both of these influence how the error covariance is updated. And so if you could have this as non-zero or you could have this as non-zero, and both of them will influence how the error covariance is changing. So it doesn't matter even if P0 is equal to 0, these things will still affect your error covariance over time.
If the sigma W I set is as a 0?
Yes. So you're saying that this is 0 and this is 0. So in that case, you have to build what is known as a Leuenberger observer. Okay, so Leuenberger observer also has a very similar sort of behavior. It becomes a deterministic system at that point of time. So you basically have the state, there is no uncertainty here, there is no uncertainty here, and suppose beta t term is not there, then you have to create what is known as a Leuenberger observer. Looks very similar. The only problem is that this particular term may not be invertible in that case. So you will have to do a little bit of mathematical stuff at that point of time to make sure that this thing doesn't cause any problem. You have to take pseudo inverse and all that stuff. So that's something that is there in Leuenberger observer theory, which again we have not covered in this class. So you take a pseudo inverse here, and what happens is along the subspace where A is stable, the Leuenberger error goes to 0. Along the dimension where the A is unstable, then depending on the C matrix and depending on the gain, you will converge to 0 error eventually. You won't have 0 error at the beginning, but eventually you will converge to 0 error. Now if you have a packet drop with Leuenberger observer, nobody has studied that particular problem. So we don't quite know how this particular term is going to evolve if you were using a Leuenberger observer with a packet drop. But I'm assuming that situation is going to be somewhat similar. Okay, because we are assuming that rho of A is greater than 1. So it's going to have very similar sort of result, which is along some dimension you may not have error, but along other dimension your error could be very large. What that implies is, let's say in a vehicle setting, you are looking at, so your state could be velocity and the distance from the center of the lane. If those are the two states, maybe your velocity you're able to estimate very well, but the distance from the center of the lane you won't be able to estimate. The estimation error along that direction could be infinity. Okay, so that could happen. Okay. So this is what my error covariance looks like. If my system is unstable, then there is a critical transmission probability, so that if I'm below the critical transmission probability, my error covariance is going to go to infinity. And that is not good for me, because that means that I'm not able to estimate the state at all. Like, my estimate is completely off from the actual state of the system. What that tells you is, if you're designing the estimator as well as the controller of a system which could potentially be unstable, so the car is not unstable all the time. So if you're driving on a straight road, the car is not unstable. But as soon as a curve comes in, the car becomes unstable. Okay, so the state space of the car, the dynamics of the car becomes unstable. At that particular point of time, you want to make sure that you are able to control sufficiently reliably and you are able to transmit observation sufficiently reliably. What that means is, around the curve, just before the curve, you need to make sure your camera is working fine on an autonomous vehicle, and your CAN bus, which is the system used to transmit control information from one place to another, CAN bus is working completely fine. Now you could have some drop in performance, which is some of the, like this beta t is stochastic or alpha t is stochastic, so that could be okay as long as your beta bar and alpha bar is above the critical transmission probability. Okay, so that's roughly what you should take away from this particular discussion, is that you want to make sure it's okay for packets to drop, but you want to make sure that even under the attack, the packet drop cannot be so bad that things become unstable and your error covariance or your state goes to infinity. Now what happens when you combine the both packet drops? So this is control and estimation over lossy network. So we did control over lossy network in the previous class. We did estimation over lossy network here. What happens if you have both control and estimation over lossy network? That is the case in vehicle, because vehicles, both estimation signal as well as the control signals are transmitted on the same communication network. So if the network is under attack, then both your control packets will get dropped and your observation packets will get dropped. So in that case, you have alpha t here, and your alpha t is Bernoulli alpha bar. And basically the only difference is in the innovation step, we will have alpha t here. Everything else remains the same. There is no difference. Everything, all this expression carries forward to that particular situation. You just have to put alpha t here, and then the main result is for this case, if rho a is greater than 1, alpha bar is less than alpha bar c, or beta bar is less than beta bar c, then PT, well, either ST goes to infinity or PT goes to infinity. So if alpha bar is less than alpha bar c, then ST will go to infinity, or rather S infinity will be equal to infinity. Or if beta bar is less than beta bar c, then PT will go to infinity. So your system will behave very badly under this particular situation. The other thing to notice here is that the optimal controller ut will be kt times x hat t given t. So there is, you estimate the x hat t separately, and then you multiply it by kt, which we had written down in the previous lecture, and that gives you your control action. So your action is always a linear function of the estimate of the state. So here we are not, this is the optimal solution. We are not actually separating the estimation and control. It turns out that separating the estimation and control is the optimal solution here, which means you can come up with the estimator separately. You can have one part of the computer just doing the estimation, the other part which is just doing the multiplication and sending the control packet. The two things can be completely separated because the two things are independent of each other. So kt doesn't depend on the estimator, and the estimator doesn't depend on the kt that is being used in this particular problem. So that's the another output of this specific result. So I think that's all I wanted to cover on this particular topic. In the next class, we'll talk about robust estimation. So now we have adversary who is introducing a lot of corruption within this particular data. So it's not a packet drop. So packet drop, we have already covered what happens under packet drop. But now the adversary wants to corrupt the state of the system. So we need to figure out what is the way to robustly estimate this x hat of t given t. So how do we come up with a robust estimation of x hat of t given t? So that's number one topic. And number two topic is to come up with a trust score. So how do we trust which sensor is giving me the right information? So that's the other topic we will study in the next class. In the class next week. It seems to me that that's pretty much all that we wanted to cover in this class. So the way we are going to move forward, next class is about robust estimation. The class after that, which is next Monday, we'll talk about trust score based methods. So there are a bunch of algorithms for trust score. I'm not sure if that will get covered within Monday or we will take to Wednesday as well. But other than that, there isn't much general technique for solving response under an attack. So I'll try to figure out what all topics can we cover on Friday's class next week. And then the week after that on Monday, my ex-student who's now working at GE Research as a cybersecurity engineer or cybersecurity research scientist, he's going to talk about what stuff he's working on. So I'm looking forward to that talk. Okay. Thank you so much, and I'll see you guys on Friday.